Percent yield. Last topic in stoichiometry. This is kind of a little add-on to the calculations that we'd already been doing. So let's start with this. Let's consider this. Imagine you have a recipe that makes 5 dozen cookies. Oh, remember dozen, that's like a mole. Mole is the chemist's dozen. So if I have 5 dozen cookies, you forget to set a timer. 15 of the cookies are burned to an inedible, you can't eat it, crisp. How successful was your cookie baking? Kind of successful? Very successful? Well, let's try to quantify this. So I have 5 dozen cookies. That's 5 times 12. So that's 60 cookies. And 15 of them we just cannot eat. How many could we actually eat? Well, that's 45. So one way that we could determine the success of our baking is to say that 45 out of the 60 cookies were actually edible, in which case we have about a 75% success rate. Or this links to our topic. What was the yield of your baking? How much did you actually successfully create? So, out of the expected 60 cookies, in theory, we should have been able to make 60 edible cookies. 45 of them we could actually eat. So, I would say that 45 out of 60 times 100%, that's 75%. I would say that my yield, successful yield, from my cookie baking is 75%. So this concept we also consider in chemistry. So think of baking cookies. It is a chemical reaction, many chemical reactions going on, but think of that analogous to carrying out a chemical change or a chemical reaction. So in theory, there's going to be an amount of product that we will create. And you folks have already been doing this via your stoichiometry calculations. And in some cases, maybe there was a limiting reactant, but those big long calculations we've been doing help us determine, in theory, how much product we would create. And we call that our theoretical yields. But then when we actually carry out the experiment, we may not get the same amount. So as a result, we can measure something, and we'd have to do this in the lab experimentally, will determine the actual yields. And if I look at that ratio and report it as a percentage, so times 100%, we call this the percent yield. And you'll see with this formula, we've just shortened actual yield into AY and theoretical yield into TY. So let's take a look at what that actually means. So a theoretical yield is the amount of product predicted by stoichiometry. So in other words, we have to calculate this. If we know how much reactant we start with, in theory, how much product do we make? The actual yield is the amount of product actually obtained in an experiment. So you have to carry out the experiment to get these values. Now, in some cases, when you carry out a reaction, the actual yield is often quite a bit less, or maybe marginally less, than what you theoretically would expect to find or create. So there's a few reasons why this might be. Number one, your collection techniques may not be fantastic. So maybe you have a solid that's formed like a precipitate, and then when you go to try and separate that out from the liquid, maybe you're pouring the liquid off, we call it decanting, and maybe some of the solid is lost in the process. Or perhaps you have several pieces of glassware that you're transferring your reaction mixture between. And in the process, you may lose some of that product. Or perhaps a gas is being created, and some of that may dissipate to the surroundings. So sometimes just the technique or equipment that we use to collect our product inherently may cause some loss. A second thing that could decrease your percent yield would be impure reactants. And in our lab, hopefully we're going to do this one when we're back in the classroom. A great example is when we use steel wool. So some reactions that we carry out may require, for example, iron. Steel wool is a mixture of iron and carbon. But when we go to react this, we presume that it is pure iron. But if there's impurities, there's other compounds. If I were to mass out 5 grams of steel wool, that's not actually 5 grams of pure iron. Maybe it's 4.95. And then there's trace amounts of other materials. This third reason might be you have competing reactions. So sometimes we have side reactions. Sometimes there's contamination in our glassware. that may compete with your principal reaction. The principal reaction is the one that we are, focused on trying to try to carry out. And in this case, you may have side reactions occurring that would cause a decrease in product. Now, I'll get you to watch this video on the Haber process. This is often called the most important chemical reaction on Earth. It's the chemical reaction that feeds the world. So it's a quick little YouTube clip, and I wanted to include this just as an application. So I'm not going to play it here, but if you pop out and watch it from the Google Slides that I've posted on our classwork. Why I include that is because we're going to look at the Haber process with this next example. So here's a sample question that involves percent yields. So we're going to be given the reaction for the Haber process. We have nitrogen reacted with hydrogen gas to make ammonia. What we want to do is calculate the theoretical mass of ammonia that could be produced. So how much product am I going to create if you start with 42 grams of nitrogen and 12 grams of hydrogen? So when we look at this, this is a stoichiometry problem. This is one that involves limiting reactant, and I know this because I have two masses given, and I have to figure out which one will run out first. So this portion of the question is no different than what we've already done. So our first step in finding the theoretical yields, well, we're going to carry out the steps of stoichiometry. So we're going to balance our equation. It's not balanced yet. We're going to find moles of both of our reactants. We'll find moles of the product, ammonia, and then let's change that into a mass. So I've worked this out step by step, and I've just kept popping the equation up at the top. So step number one, let's balance the equation. You can try this, pause the video, and then come back and make sure you have it balanced. And then you're back, and it's a 1:3:2 ratio. Okay, so step number one, let's find the ratio in which reactants and products are present in this reaction. Okay, step number two. So this is a really good review of limiting reactant. We're going to calculate the mass of ammonia produced, but the first thing we're going to do is take each of our reactants and we're going to change it from a mass, 42 and 12 grams, just into a molar amount. So notice here for nitrogen, it's N2, and I'm getting that directly from the chemical in the equation. So I've done 2 times 14.01 to get the molar mass. And then I'm going to do this again for hydrogen. I have H2, so 2 times 1.01. And then we'll divide. We're going to keep a whole bunch of digits. And at this point, you can see our amount is now just changed from grams into moles. Now, which one's going to run out first? Just by looking at these numbers, we can't say that, oh, it must be nitrogen because it's a smaller number. Keep in mind, it has to react in a 1:3 ratio. So our next step, we've got balance, moles. That was moles of what was given. Now we're going to go to moles of what's required, and that's our ammonia. So you'll notice here, I'm going to do this twice, and I've put this little versus sign between them. So if my nitrogen, that amount, were to be the one that runs out first and be the limiting reactant, this will determine how much ammonia I could make. I've set up my mole ratio. What I'm trying to find, my required, that value goes in the numerator. That 2, just to remind you, came directly from the balanced equation. And I know for every 1 mole of N2, I'm going to create 2 moles of ammonia, so twice as much. Ignore the red for a moment. I'm going to do the same thing for hydrogen, presuming it's the one that runs out first. And the ratio here, for every 2 moles of ammonia that I'm going to create, I would have needed 3 moles of hydrogen. So my mole ratio here is 2/3. What I'm trying to find up on top, what I'm converting away from, or what's going to cross out in terms of units, goes on the bottom. And now I have moles of ammonia and moles of ammonia. Now I can look at these two and I can see that the first value is smaller, so the smaller amount of product is going to be created based on the fact that I'm starting with 1.49893 moles of nitrogen. So I would say that nitrogen, N2, this was the reactant that made a limited the amount of ammonia created. So I've just highlighted in red here the limiting reactant. So once I've used up the 42 grams of nitrogen gas, this is how many moles of ammonia. Our last step, let's convert that ammonia from an amount in moles into a mass. So I'm going to use the same formula, moles, that was our moles of ammonia in red, times the molar mass of NH3. So 1 nitrogen, 14.01, plus 3.03 grams of hydrogen, and our final mass would be 51.1. So this is a stoichiometry problem with limiting reactants. It's what we've already done, but what you've essentially determined here is the theoretical amount of ammonia that could be created based on these two amounts of starting materials, nitrogen and hydrogen. So that's our theoretical yield. In theory, if everything went perfectly, this is how much ammonia we should create. Now, if we wanted to find the percent yield, we need to be given one more piece of information. We need to be told how much was actually made in the lab. So I'd have to give you, or you'd have to experimentally determine this, but let's, for argument's sake, say that 32.9 grams of gas was actually yielded or created. So that's my AY. To find my percent yields, how well did I do at this reaction? 100% is great, but usually it's not going to be 100%. I'm going to take the amount, the actual yield, divided by, in theory, what I would have expected to create. Multiply it by 100%, and then you could see for this one, 64.4% would be my percent yield. So not a great yield. So maybe something happened. Maybe it's a gas, so maybe some of that escaped due to our collection techniques. Or maybe there were some contaminants, or maybe we didn't have quite as much nitrogen or hydrogen as we thought present. Maybe there's some impurities contaminating those gases. Okay, now in some industries, chemists know what percent yield to expect from a given reaction, and that's because we've carried out these reactions over and over and over and over, and data is often collected, and we can generally say with a amount of certainty that this reaction tends to have about a 83% yields. So by examining certain reactions, we know what to expect. So the second example is how you can predict the actual yield based upon the percent yield. So let's use this one. This is calcium carbonate. This is like limestone or marble. And this will decompose into calcium oxide and carbon dioxide gas. Now, under a specific temperature pressure, this reaction has been known to yield about 92.4%. That's the percent yield that we can expect over many, many rounds of examining this. How many grams of calcium oxide could be expected then if you start with 12.4 grams of calcium carbonate? So now it's kind of saying, well, what could you actually expect to get? So first thing we're going to do, we know we have a mass of 12.4 grams. Let's find our theoretical yield. In theory, how much calcium oxide could I create? So here's our steps of stoichiometry again. Number one, let's balance our equation. And it's a 1-to-1-to-1. Step number two, let's take the mass of the reactant, 12.4 grams of CaCO3 of this marble, and let's change that to an amount in moles. And this molar mass, a calcium, a carbon, and 3 oxygen. There we have it. So that's how much calcium carbonate we have to start with. Let's find the amount of required, which is my calcium oxide. So I have 1 mole to 1 mole ratio. So I can expect to produce the same amount in moles of calcium oxide when 12.4 grams of calcium carbonate decompose. And then my final step, let's change this into a mass. So moles, and then there's the molar mass. So in theory, with those 4 steps of stoichiometry, didn't have to worry about limiting reactant this time because we only had 1 reactant. I would expect 6.95 grams of calcium oxide to be created. So that's great. That's in theory how much we should expect. Now, you're also told under specific conditions that this is 92.4% successful. So what we're going to do, in this case, to find out how much is actually made, what we could expect in the lab, we're just going to rearrange this equation to find actual yield. So let's get this AY on its own. I'm dividing by TY. Let's multiply by that on the other side. So percent yield times theoretical. I'm multiplying by 100. Let's divide by 100 to move that to the other side. So here's my rearrangement to find actual yield. Now we're going to plug in our values, 92.4% over 100, 6.95, and here's our actual yield. So based on this success rate, we can expect to create 6.42 grams of calcium oxide. So that's just a little twist to that, and just some practice rearranging this equation. If you have any questions about that, let me know. So generally you find these kind of tacked on, these percent yield questions tacked on to the end of a stoichiometry or limiting reactant problem. It's just kind of one extra little step. And if anytime you're being asked to find theoretical yields, really what you're asked to do is carry out the steps of stoichiometry and then use this little equation to determine how successful your experiment was. Okay, if you have any questions, please email me and let me know.